Hello, just thought I'd drop in and welcome to my channel. This video is about antennas for the 23 centimeter amateur band or 1296 megahertz, and there aren't very many commercially available antennas at all. So I've borrowed a selection from some friends and thought I'd just compare them. I can't make any accurate measurements, of course, but I'm going to try just to make some relative comparative measurements using a network analyzer, VNA, the Nano-VNA. It's a vector network analyzer, but we're not looking at Smith charts today, don't worry. What I'm going to do is I'm going to use this as a transmit antenna. This is a discone antenna that has a relatively flat frequency response. It doesn't matter because I'm not going to measure over a frequency band, I'm just going to measure at a single frequency, around 1296 megahertz. And what I'm going to do is I'm going to test each antenna in turn, connecting it to the other end of the cable. This cable is probably 3 meters long, I have to check. First thing I'm going to do is calibrate the cable, or calibrate the VNA against this cable so it looks like 0 dB insertion loss. So what I'll see is the real path insertion loss between the test antenna and this transmitting antenna here. Now the antennas I'm going to test, the most bizarre one is this homemade coffee can antenna, which has a connector on the side, an SMA connector here, and inside there's just probably a quarter wavelength radiator and another rod on the other side which can be adjusted to tune it. And this should work quite well. It has a very good front to back ratio because not much signal will come out the back of this. So that's the coffee can antenna. These are not in any particular order. This is an antenna that looks similar to the HP9CV design, which you might know. It's very small, it's just made on a printed circuit board, but it really seems to work very well. It came with a transverter kit that was bought from somebody in Bulgaria who makes these. So it's nice to test. Also, I've got this. This is a homemade Yagi antenna that somebody's very kindly loaned me. You know who you are. And I'm going to test this. So this is a very directional antenna, a Yagi or Yagi. I have to ask in Japanese how to pronounce that. What else have I got? This was loaned to me by somebody. This is a 1.3 gigahertz RHCP, whatever that is. It's allegedly an antenna. Oh yeah, right-hand circular polarization. So it's not vertical. This is probably coax feeding up to it. The thing at the top has some kind of a circularly polarized radiating element, so you have to point it in the direction of where you want the signal to go, like this, and it'll send a right-hand circular polarized signal, so I'm going to try that. Also, I have this, which is a home modified antenna. This was a 868 megahertz ISM antenna. It actually came out at 915, and if you watch my previous videos, you'll watch me test it after I soldered a bit of wire on the end to drop the frequency down to 868. What I've done now is I've trimmed it. It's actually a vertical sleeve dipole. If I take that off, you can't quite see it. I'll show you these under the closer camera in a moment. But it's a brass sleeve, and that's the inner of a piece of coax, which I've trimmed, again, much shorter to be resonant at 1296 megahertz. You have to measure it when you put the cap on, because that changes the frequency a lot. And then the last one is this, a diamond tri-band antenna, which is a very small stub antenna, which allegedly works on 144, 433 and 1296 megahertz. It's not an original diamond antenna, I'm sure, because it costs 5 times less than a real one would, or even cheaper. Came from Amazon. It's obviously a Chinese knockoff copy of the real thing. They didn't put the diamond logo on it, but I don't think Diamond themselves would be proud of this antenna. But I'm going to test it anyway. The VSWR is awful in most frequencies except for 433. So I think that's all the antennas I intend to test in this simple test. What I'm going to do now is switch over to the other camera, which is going to be looking down on the screen of the VNA. And I'll calibrate it quickly. I'm only really interested in the path loss on the coax being calibrated out. I'm not going to make VSWR measurements. So I'm just going to calibrate the S21, which is the forward transmission to this is the where's the transmit port? This is going to be the transmit port, which is normally the test port for S11. And then the signal is going to go down this one piece of coax, up the other side and back into the measuring port. And then when I've calibrated, I'm going to disconnect it, and I'm going to connect it to each antenna in turn, put it on the other side of the room in the same spot, maybe move it around a bit and see see what the signal strengths look like or what the attenuation is read on the VNA. So now I'm going to go over to calibrate the VNA. So here's the VNA, and I'm going to calibrate so that we can compensate for this long length of coax here. Can't move it any closer to the camera to make it bigger because it won't focus, so that's that. How do we calibrate this? Press calibration, calibrate. Open and short I've already done, probably. Load and isolation. What I want to check is through, or I want to calibrate through, so I'm going to click on through, and it's going to make a through measurement, and then hopefully it will be able to calibrate that out. What I need to do is to save it by hitting done and choose where to save it. That one, 50 kilohertz to 1.5 gigahertz. So now you can see this straight blue line. Ignore the yellow one, that's S11 or VSWR. We're not really interested in that, although it looks pretty flat. It goes up to about 1.4, 1.5. This is this little blue triangle here, if you can see it, that's the zero line. So now we can see 0 dBs insertion loss across the whole frequency range of 50 kilohertz to 1.5 gigahertz, which of course is not the case for the cable, but that's been subtracted out to make it look flat. So now I can make some more meaningful antenna measurements. So that's calibrating the VNA. What I said I'd do is I'd show you these antennas a bit closer. So this is the HB9CV kind of, I'm not sure if it really is an antenna, printed on printed circuit board. It works extremely nicely. And I've contacted some stations not so far away, but it radiates the signal beautifully and it matches beautifully, so I'm very happy with that. This is my modified ISM antenna, so it's the sleeve dipole, where it's just a piece of coax and the inner of the coax is used as the radiating element. I'm going to trim the length of this because it's too long. This is the thing that's a circularly polarized antenna for drone controllers, maybe. Be interesting to try that. That came from AliExpress, I hear. So the other one that was a bit small is this allegedly diamond, but I'm sure it's not, SRH 805S, which is supposed to work on every frequency under the sun. So let's try those and see what kind of results I get. I was having to work out a way of seeing the screen from the other side of the room where the receiving antenna is going to be, and I found some more antennas to test. So I'm going to test this one. This is a homemade ground plane. I'll show it closer perhaps. Just a quarter wave ground plane with radials that I made, soldered onto the back of an N-type connector, so I'll be testing that one. And another one, lent by a friend, which I completely forgot about until I found it, is a collinear. It's about 1.2 meters long maybe. Homemade collinear antenna in a plastic tube, and I'll be testing this as well. So what I'm going to do next is to connect these antennas to the other end of the coax and the receiving end, and then the signal will come back here to be measured. Problem is, from the other side of the room I can't see the screen on the VNA. If I'm using a spectrum analyzer, unfortunately mine only goes up to 1 gig, not 1.2, or it's 900 megs. Then what can be used on the spectrum analyzer, you can switch on a big display, big numbers you can read from a distance away of loss in dBs. Unfortunately, the VNA, I can't find that setting, so I don't think you can have a big display. What I've done is I've set it to 0 span, because I'm not interested in a span of frequencies, so 0 span with a center of 1296 megahertz. So I just see a blue line that's steady and goes up and down according to the loss on the path between the two antennas. So let's see if I can manage to measure this. I tried using a little telescope, but it won't focus that close. I tried using a mobile phone to view it from a distance, and it's just too fuzzy, low resolution on the phone camera. So let's see how I get on with that. Another thing I noticed is that I can read the height of the line, which I can see from the other side of the room. You can tell this is getting serious because I had to turn the light on. And what I'm doing is I'm walking around, and you can probably see that as I move near the antennas, the line goes up and down because of reflections from my body, multiple reflections and cancellations. So this is going to be a very rough measurement. This here is saying 10, 20, 30, 40, minus 40 dBs. So there's 40 dBs of insertion loss between this discone antenna and the tiny ground plane at the other end that I found just a few minutes ago. So 40 dBs, that's going to be my kind of reference maybe. It dips down to 50 depending where I stand, but the best signal I can get is -40. If anybody has an anechoic chamber they want to donate, then you know where to send it for antenna measurements, please. Here you can see the receiving end of the link. This is the tiny ground plane I showed you earlier, quarter wave ground plane made with some brass wire soldered on the back of a socket. This is my antenna mast, not the biggest mast in the world, but it's good for tabletop stuff. So, as I said, testing this, I got about a 40 dB path loss. That was the best path loss, going down to 50 dBs when I moved around. What I'm going to do now, I think, is test this antenna just to make sure that the test range is working, because this antenna probably has 10 dBs more gain than that one, or something like that. I'm only guessing. Let's see how that antenna performs. So now I've put on the Yagi antenna, remembering to have it vertically polarized because the discone at the other end is vertically polarized, and I can watch the blue line go up and down on my VNA, and when I turn the antenna you can see it's very directional. The signal level drops down very fast when I rotate it, which is a good sign because it means the antenna is working. It's concentrating the signal in one direction, and by concentrating in one direction, narrowing down the beam width, this means it has gain. So as you'd expect, this beautifully constructed antenna has gain. Don't worry, I'm not going to adjust the tweaking capacitor on it. This is getting overexposed on this camera, isn't it? Oh well. This is, again, when I move around, the level goes up and down. The best signal level I can get is -35 dBs. And with the little ground plane it was -40. So what that means is that, just as a rough estimate, this Yagi has got 5 dBs gain more than the ground plane. I would have expected more, but I don't think I've got the best test setup. And when I move around, it does make a big difference, about 5 or 6 dBs as I'm walking around the room. But it looks like the, let's just talk about path loss. It's 35 dBs instead of 40, so it's certainly got 5 dBs gain, probably more. So now that I know the test setup is showing whether an antenna has gain or not, I'll try the other antennas. Now I put on the little stub antenna with diamond written on it, and this really has gone down to only just above the noise floor of the analyzer, and I'm seeing, if I move around for the best signal, -50 dB, so 50 dB path loss, or a bit more, which is, showing it's not the best antenna at this frequency. It's giving 10 dBs worse performance than the homemade ground plane. At least 10 dBs worse. But it's a broadband antenna, so you can't expect it to be optimized like this tuned antenna is, so maybe 10 dBs worse is acceptable. This now is the vertical dipole without its lid, and it's showing -40 dBs. It's less sensitive to people moving around the room, so it's down at 40 dB insertion loss, the same as the ground plane. I have to remember to put this on because this detunes, lowers the frequency to be correct. I cut the element inside to be correct when the plastic top is on, of course, and it's still 40 dBs down. So it's the same as the ground plane. Putting on or taking off the plastic doesn't seem to make much difference to the signal strength, but what I know it does is it changes the SWR. When you measure the SWR, then you see it's important to have the plastic on because it's been cut for that. So that's that stubby antenna. Now I've put on the HP9CV antenna, or lookalike, and that's giving me -40 dBs as well. And it varies as I move around the room, more than it did with the monopole antenna, but it's fairly consistently -40 dBs. And if I try rotating it, the signal level drops, but not nearly as fast as it did with the Yagi, which is what we'd expect. So it's less directional than that 5-element Yagi, is it? 1, 2, 3, 5, 6-element Yagi, sorry. And you'd expect it to be less directional. So the beam is wider beam width, which means the gain is less. And it looks like it's approximately the same as the ground plane, but then it's hard to see because these are weak signals. It's not a calibrated setup. There's a lot of reflection, so it's around about 40 dB insertion loss on the path between the two antennas. Now for the fun antenna. This is the circularly polarized antenna for drone controllers. and of course I've got it pointing at the receiving antenna. Actually, it's the transmitting antenna. This is the receiving antenna. It doesn't matter because of the theorem of reciprocity. The attenuation is the same along a path in both directions. And this is, when I move around, the best signal I can get is minus 50 dBs. So 50 dB path loss. Check that. 10, 20, 40, 50. Yeah, it's around about minus 50 dBs, which is 10 dBs worse than the ground plane. But remember, this is circularly polarized and the antenna at the other end is vertical, so there's going to be some loss, some cross-polarization loss there. But it seems to be about 50, minus 50, so 50 dB attenuation on the path. If I'm very careful, I can actually get a slightly better reading, a bit higher, maybe 47 dBs, as I move around with reflections. And of course, reflections make a huge difference to these kinds of measurements. So what I'm doing is actually meaningless in terms of lab measurements, but it just gives an idea if an antenna works or not. And it looks like this is 10 dBs worse than the homemade ground plane. I haven't checked the SWR yet to see if it's tuned at all at 1296 megahertz. How many antennas have I tested? 1, 2, 3, 4, 5, 6. That's number 6 antenna. And then the number 7 antenna is going to be the long collinear, which I'm going to have to put on the floor, I think. Now I've put the collinear antenna on here to measure, and of course it's not fair because it's close to the table here. I've tried to keep the distance roughly the same to the transmitting antenna and raise it up a bit as well. If I move around, the peak value I get is minus 32 dB, so the path loss when I'm standing in the right place is only 32 dBs. So that's 8 dBs better than this ground plane, which was 40 dB path loss. So this is minus 32. It looks like 8 dBs of gain over the ground plane, but again, it's very subjective. It's all relative, but probably minus 32. And perhaps not quite as good as that, but it's interesting because it's obviously got gain. I don't know how many elements are in here. I'll ask the owner, and I'll put that in the description. But it certainly works, and even when it's close to the table, which has a metal piece underneath, which I'm sure is detuning it. So it looks like minus 32 dB, which is impressive. Wow. There's one last antenna I forgot, and I'm going to test that one next, which is a surprise antenna. This was number 7, by the way, the collinear. Let's try number 8. Just quickly before I change antennas, I just put it back on the table, and the signal levels drop right down, because of course this is the height of the antenna at the other end, and this collinear is well over 1 meter, maybe 1.5 meters high. So most of the energy is radiated from far higher up. So that's increased the distance, and also because of the gain, the radiation angle vertically, the beam width is quite narrow. So it needs to be lower down, back down on the floor, so that the center of the antenna is at the same level as the antenna at the other end of the link, and then that was where I was getting the 32 dB path loss. Now it's gone down to about 50 dBs. So of course you have to adjust the height as well. Anyway, let's try the next one. This is antenna number 8. It reminds me of something. I think the spot lamp on a ship you could use to signal to other ships with the shutter on the front. But anyway, it's a coffee can antenna, which might have been a paint tin, and with that little quarter wave radiator inside. Is it painted inside? I don't know. It seems to be a darker grey colour inside. And sorry about the overexposed video. For some reason, the auto exposure is not working on the camera. I'm too lazy to change it. Anyway, this is giving a path loss of, at best, when I move around, the best is about 35 dBs. So a 35 dB path loss, and the ground plane was giving 40 dBs. So it looks like this has 5 dBs gain over this ground plane, which is nice. So it's complicated, it's all waveguide effect, but it's very directional. If I rotate it, the signal level drops off quite quickly. It's like the Yagi antenna, this one, in terms of having a narrow beam width, which is what you'd expect, because you can see that the signal is going to come out in a beam from the hole and not spread out so much. So this works really nicely. It's very stable as I walk around as well. So this is because it's not being affected by reflections from me going around behind the antenna and entering from behind, which causes more complex interference patterns. Because it's really narrow beam, it's kind of ignoring me, and reflections are only going in there when I move around. So there we are, minus 35 dBs. That's nice. So I think that's 8 antennas now that I've tested. Thank you to all the people who lent me antennas, 2 of them I think, and don't worry, I'll give them back. and I didn't try to change them anyway. So I'm going to say thank you for watching the video. Please make comments and suggestions in the comments below, and ideas for more videos. This is the first time I've really used 1.3 gigahertz, just in the last couple of weeks, and it's an interesting band to experiment with. What I do notice is at the moment I have indoor antennas, and if you are communicating with another station, if you move the antenna just a couple of centimeters, the signal level goes really right up and down because of the reflections. So maybe on an outdoor antenna that would be less of an effect, but indoors certainly the walls and windows and everything are causing different reflections and interference, constructive and destructive. So you really have to position it in the right place for the station you're talking to. If another station comes on, then you have to move the antenna to receive that one nicely. Whereas probably an outdoor antenna would be better. I'll try that sometime when the rain stops. So that's all I wanted to say about antennas. I hope you found it interesting. And please remember, this is only a very, very rough measurement of relative gain, kind of, in a very bad reflective environment. So don't take it personally if your antenna didn't come out as the best, because maybe in free space it is the best. But this is in a reflective room test scenario. Thank you for watching. If you liked the video, please press like and subscribe if you'd like to be informed when I next upload a video.